Chapter 2 to 4. Single AI, Selective Recognition Flow. Multiple AIs employ a recognition process that starts with broad scopes and gradually narrows down to improve accuracy. Similar to how humans refine their recognition scope. In my AI recognition design, I integrate this principle. To elaborate, let's delve into the task flow for selective recognition. Starting from a single AI to multiple AIs. Chapter 2 to 4. Recognition Task Flow. AI training involves 3 steps. 1. Creating recognition paths for individual labels. 2. Expanding these paths into recognition scopes, and 3. Storing numerous recognition scopes in AI neural networks. AI training begins by assigning labels to samples and forming recognition paths as seen in this figure. Multiple samples under the same label enhance recognition likelihood, establishing scopes. Storing these scopes in neural networks completes one-dimensional AI as seen in this figure. During AI testing, the AI picks the label with the highest probability from its stored recognition scopes, as depicted in this figure. If the object doesn't match learned labels, as seen in this figure, the AI still chooses the label with the highest probability, without checking if it matches any learned label. This can cause repeated recognition problems. Chapter 2 to 4. Selective Recognition. AI doesn't have a penalty for its incorrect recognitions, as there's no high-authority AI to assess its judgments. This results in persistent errors and recurring issues. To address this, I introduce a new concept, no recognition. To implement this, I utilize prediction confidence, based on softmax, in AI recognition. This enables the AI to selectively recognize objects with high confidence values, while no recognition in the other cases. For example, in this figure, the AI mistakenly identifies an object as vehicle for the test image, motorcycle, due to the absence of the correct label. However, in this figure, recognition is suspended for the test image, because the confidence level, 66%, falls below the threshold, 95%. Chapter 2 to 5. Recognition from broad to narrow scopes. In my AI recognition design, when different level single AIs recognize the same object, I rank them based on their predicted probabilities, as shown in this figure. Essentially, higher-level AIs guide lower-level ones, like a parent guiding a child. To confirm a recognition decision, all AIs must exhibit at least 95% confidence in their identification of the same object. Firstly, I give priority to single AIs based on their predicted probabilities, starting with the grandparent-level AI, which has relatively fewer labels. For example, in this figure, I separated the same samples into 8 grandparent labels and 144 parent-level labels. From the 2 pie charts, the case of the grandparent level, 1 of 8, has a relatively higher likelihood of accurate recognition than the parent level, 1 of 144. Secondly, I arrange single AIs based on their confidence values, starting with the grandparent-level AI. In this figure, the confidence value represents the label with the highest normalized probability among predefined labels. As illustrated in this figure, the grandparent-level AI achieves higher confidence due to its fewer labels, resulting in less label overlap during confidence assessment compared to lower-level AIs. Chapter 253. Recognition from broad to narrow scopes. Third, I prioritize the grandparent-level AI in my AI recognition design due to its broader recognition scopes compared to the other AIS. As shown in this figure, a grandparent label includes many parent labels, and each parent label contains various child levels. This means that I prioritize multiple AIS with broader scopes first and then move to those with narrower scopes, following a step-by-step approach. Chapter 254. Recognition from broad to narrow scopes. Fourthly, in multiple AI scenarios, I give preference to the AI with recognition scopes containing more samples per label. This boosts the likelihood of finding similar samples for accurate object recognition. For instance, as illustrated in these figures, there are more samples associated with a single label at the grandparent level, over 1,000 samples, followed by the parent level, over 500 samples, and the child level, over 50 samples. Consequently, higher-level AIS are more inclined to be recognized with higher confidence for test samples. Chapter 255. Imbalances in sample numbers per label. When a single AI has varying sample counts per label, labels with more samples are more likely to be recognized accurately. To address this, I implemented a mitigation strategy. I cross-validate single AIS with different sample counts per label. If there's a recognition discrepancy between linked higher and lower-level AIS, the recognition result is rejected at the current AI, and further recognition is paused. Probabilistically, utilizing cross-validation across the three levels of AI proves more effective in mitigating the side effects of imbalances in sample numbers per label, compared to solely relying on a single AI.